Hello everyone and welcome back. This is Mr. Cobalt, and in this video I'm going to be going over a short history of the development of the atomic theory. How did we get to where did we come from as far as our model of the atom, and where have we gotten to? And so we're going to start with John Dalton. So John Dalton is the father of the modern atomic theory. The atomic theory actually goes back to early Greeks. First Greek that comes to mind is Democritus. He actually came up with the original idea that all matter is made up of atoms, and then John Dalton, much later on, resurrected that idea. So here we have John Dalton's model. He believed that the atom was an unbreakable solid sphere. There was no parts to it that could be broken apart. He also held that all atoms of the same element were the same size and properties and things like that. But those turned out to be actually false. So, where was Dalton wrong? Well, he believed that all atoms had the uh, same mass, but in fact, all atoms have an average mass. The mass on your periodic table is an average mass of all of the naturally occurring isotopes for that element. So different atoms of the same element can have different masses, and that's because of the neutrons, the particle in the nucleus. You can have more or less neutrons for that element. You can't change the number of protons. Uh, so, so Dalton was mistaken on that point. Also, he said that atoms cannot be divided, created, or destroyed during at all. But actually, atoms, it's true that atoms can't be divided, created, destroyed during normal chemical reactions, but they can and do during nuclear reactions. So, nuclear reactions, as the name implies, are reactions that involve the nucleus. And so, you can divide the nucleus, you can combine nuclei of different atoms. And so, Dalton was mistaken about that as well. All right, so in our progress towards developing a better model, we discovered, or not we, but it was discovered by J.J. Thomson that there were particles in the atoms, particles that were smaller than the atom itself and that had charges. So J.J. Thomson used what is called a cathode ray tube, which is this thing right here, and he was able to deduce the presence of a negatively charged particle. Well, how did he do that? Well, you have basically a vacuum inside the tube, and so there's no air in this. And what you did is, at least you have this wire, and you have a voltage source connected to the wire. So basically, you're running electricity through this. And so what happened was when they connected this up, you got basically a ray that would go from one side to the other. So from one electrode to the other. And so what he did was he put some positive and negative plates on either side of the tube. And what he noticed, for any time he did this experiment with any substance whatsoever that he was able to do it with, he found that whatever this was, it bent towards the positive plate, and it bent away from the negative plate. Well, as we know today and as they knew then, negative same charges are going to repel, and opposites are going to attract. So this was being attracted to the positive plate. So the conclusion is that these must be negative in nature. So this became the discovery of the negative particle that all matter seems to have at that point. And so that was the discovery of the electron. So cathode ray tubes are going to pass electricity through a gas that can be contained at very low temperature, or pressure. And here's a link to a video if you want to watch that. All right, so what are the conclusions we can draw? Well, cathode rays have identical properties regardless of the element used. So whatever element you use, we got the same properties. We got the same negatively charged particles. So all elements must contain identically charged electrons. Okay, so because all elements that was tested had that same cathode ray effect. Atoms are neutral. We know that atoms are neutral. So therefore, we know that if there's a negatively charged particle, there must be a positively charged particle balancing the negative charge of the electrons. And electrons have very little mass compared to the atom's mass. So atoms must contain other heavier particles that account for most of the mass of the atom. So those were the conclusions that we could draw from the fact that we discover this negatively charged particle. All right, so Thomson's atomic model. What was his model? Well, his model is often referred to as the plum pudding model. And so you're probably wondering what plum pudding is. Well, this picture down here gives you an idea. So plum pudding is basically bread with raisins baked in it, or or what are called plums in the UK. So what they call plums is what we call raisins. And pudding is not what we call pudding here in the United States. It is actually just bread. So here's you get an idea. So for his plum pudding model, what he thought was, if you see in the bread here these dark spots, he believed that the electron, this negatively charged particle, was embedded in a kind of positive stuff, just like the raisins here are embedded in the bread. So the surrounding bread would be your positive stuff, and the dark raisins would be your electrons embedded in that. And so that was his idea of the model. So that's how he was accounting for these negative charged particles. Okay, so so that explains what his model was. That's the model he came up with. So we went from a solid sphere in the Dalton model to now a plum pudding model that has negatively charged particles embedded in this positive stuff. So this is another picture of it. So you have these negative electrons, and then you've got this positive pudding or stuff that is surrounding the negative electrons. So the negative electrons are embedded in the positive stuff. All right, so next in our steps towards developing the model, we come up with Rutherford. So Rutherford's gold foil experiment is another famous experiment. And so what you can see here is that Rutherford decided that he would take a very thin gold foil, and then he would take a alpha particle emitter, and an alpha particle is just a helium atom without the electrons. So it's just a nucleus, a helium nucleus, and so it's a very large, very positive charged particle. So what he decided to do is he would decide to shoot the alpha particles towards the gold foil, and he wanted to know what happened. And so he put a detecting screen around the gold foil. And what he noticed after the experiment is that you would get these light spots on the screen, and that's where the alpha particles hit. And the amazing thing that he discovered is that although over 90% of the alpha particles shot right through and didn't really deflect much at all when they went through the gold foil, um, much to his surprise, you did get large deflections every now and then, almost right back at the alpha emitter. So some of them even bounced back towards the alpha emitter. And so you could see here this really large deflection. So what does this mean? Well, this means that he concluded that if Thomson's model was correct, because we know that electrons are so very small, and the plum pudding model says that most of this is space, you should get 100% of the particles, or very much close to 100% of the alpha particles, just blowing through the atoms. But because you get this very large deflections from the alpha particles as they go through the gold foil, this indicated that there must have been some very large, dense part of the atom. And this large, dense part had to be positive because, again, he's shooting positive particles into the foil. And so we know that positive charges repel. So this deflection must be due to a very dense, positively charged part of the atom. And so that's what he called the nucleus. And so for his model, which is this model on the right, is the nuclear model. So he is the father of the nuclear model. So it has a nucleus that is very dense and positive, and this is where almost 99% of the mass of the atom is located. And as you can see, the electrons are on the outside. The electrons are very small, but you'll notice that the atom is very much mostly space. So compared to the Thomson model, where this is filled with positive stuff, there is no empty space. This is empty space. So that is the Rutherford model. And again, we have a YouTube video for that here if you want to check that out. So what is Rutherford's findings? Most of the particles pass right through. A few particles were deflected. A few were greatly deflected. And so the conclusion is that the nucleus is small, so there must be this nucleus and it's small. And the atom is mostly empty space. So you have a small, dense, positive nucleus, and most of the atom is empty space. And the nucleus, as I said, is dense, and the nucleus is positively charged. So those are the conclusions that we can come to. Next is the Bohr model. So Niels Bohr comes along. We still have our nuclear model, but he kind of changed it. And he asked, well, how are the electrons, how are they in this atomic model? And so we have the nuclear model. And so for him, the electrons for excuse me, for Rutherford, the electrons were more like this, going around the atom in any which direction. But you can see here for Niels Bohr, he had kind of what is called the solar system model. Each electron or set of electrons were in their own orbits. So they are traveling around the nucleus like planets travel around the sun. So the electrons had their own path around the nucleus. And so we usually draw the atoms like this, with the electrons going around the atom like planets around the solar system, but this is not the accurate model. This isn't an accurate model. We use it a lot because we can use it to simplify and explain things more easily, but this is not correct or as accurate as we would like. So now comes the last step so far. I shouldn't say the last step. It's the step that we're on in our development of the atomic model, and that is the quantum model or the quantum mechanical model. And here, I'm not going to try to explain it in this video, but we've gone from solar system model where the electrons are traveling in nice circular paths or orbits around the nucleus. But for the quantum model, it's more like a cloud of where they travel in clouds, and that's not the best way to put it. But this is a three-dimensional model, and so you can see that there are these shapes inside. You got the spherical shape, you've got this dumbbell shape. It looks like two balloons put together end to end. And these are what are called orbitals, not orbits, but orbitals. And so, what is an orbital? Simply put, it is a statistical probability map of where one is going to find the electron. In the quantum model, or according to the quantum model, we don't know exactly where the electron is, and we can't know exactly where the electron is. All we can know is that it's probably within this space, about 90% probability, right? And that's what we call the orbital. So this space here, you can see this circle here, this bluish circle there. That is called the 1s orbital. And so that orbital is the space, the probability space of finding the electron within that space at a certain energy level. If you go to the second energy level, you go to a higher energy level, you get the 2s orbital, and that orbital is bigger, same shape, but bigger. And so you can see that the space, the probability space of finding the electron is here. And that's all we can really say at this point, is that the electron, if you have an electron in the 3s orbital, all we can say with 90% probability that the electron is somewhere within this spherical space. If you're in the 2p orbitals, you notice the p orbital looks like two balloons put side by side, connected at the end, right? So this is a 2p orbital. And again, if you have an electron in what is called the 2p orbital, it's all this is the probability of finding the electron in this space. So this three-dimensional dumbbell-looking space is where you have a high probability of finding the electron in the 2p orbital. And that's really, well, all we can say. So when we're thinking about the Bohr model says that we do know where the electrons are. They're on these circular paths, and we can point to where they are on that path. But the quantum model says, no, that's not right. We actually don't know where they are. We can never know really where they are. We can just know where they probably are. And that's really as far as we're going to go in this video. I hope you enjoyed this video. I know some of this last stuff was kind of hard, but if you enjoyed this video, please make sure you like, share, subscribe to my channel, hit the notification bell, and also put a comment in the comment section. Let me know what you think. Ask me questions. I love questions. Thank you very much for joining me, and have a great day.